Hi there. This is a talk I was doing for the Clydesdale Astronomical Society. I'm not an expert in astronomy, and I'm not an expert in planetary science, and I'm not an expert in geology. But I'm quite interested in all those subjects. So I'm kind of hoping that I'll maybe find something in tonight's talk that you find interesting. Anyway. Mars isn't called the red planet for nothing, even though a small telescope is undeniably red. However, this talks about the geology of Mars, and the one thing geology does better than any other science is deep time. In other words, if you want to find out why Mars looks like it does today, you need to understand what it was like a very long time ago, say 4 billion years ago, in fact. At the time, the Earth looked like this. Earth certainly wasn't the pale blue dot we know and love today. But how about Mars? We think this is how Mars looked 4 billion years ago. You could be forgiven for thinking this is actually a pretty rubbish artist's impression of Earth. The first part of this presentation is going to be about what we've discovered that makes us think Mars used to look much like Earth today, and what has happened in the meantime to change Mars into the desert planet it is now. The Mars ocean hypothesis proposes that the Vasstitas Borealis basin was the site of an ocean of liquid water at least once, and presents evidence that nearly a third of the surface of Mars was covered by a liquid ocean early in the planet's history. This ocean, called the Oceanus Borealis, would have filled the basin in the northern hemisphere, a region which lies 4 to 5 kilometres below the average planetary elevation. 2 shorelines have been suggested, a higher one dating to a time period about 3.8 billion years ago and concurrent with the formation of valley networks in the highlands, and a lower one, perhaps correlated with the younger outflow channels. The higher one is called the Arabia shoreline and can be traced all around Mars, except through the Tharsis volcanic region. The lower one is called Deuteronomus, and it follows the Vasstitas Borealis formation. A study in June 2010 concluded that the more ancient ocean would have covered about 36% of Mars. So that's the theory. Where does the evidence come from? On November the 7th, 1996, the Mars Global Surveyor mission was launched. The purpose of the mission was to orbit Mars and map it over the course of approximately 3 years, which it did successfully. And actually it survived past this allotted span to complete 4.5 years of mapping. This is a picture of the Mars Orbiter Laser Altimeter, or MOLA, which did the actual mapping. Generated by the MOLA, this high-resolution map represents 27 million elevation measurements gathered during 1998 and 1999. The data is assembled into a global grid, with each point spaced 60 kilometres apart at the equator and less elsewhere. Each elevation point is known with an accuracy of at least 13 metres, with large areas of the flat northern hemisphere known better than 2 metres. An impact basin deep enough to swallow Mount Everest and surprising slopes in the Valles Marineris highlight a global map of Mars that has aided scientific understanding of the red planet for years. And using the data from the MOLA map suggests that the watershed for the Oceanus Borealis would have covered 75% of the planet. Early Mars would also have required a warmer climate and denser atmosphere to allow liquid water to exist at the surface. In addition, a large number of valley networks seen on the MOLA map strongly supports the possibility of a hydrological cycle on the planet in the past. In 1971, the Mariner 9 spacecraft caused a revolution in our ideas about water on Mars. Huge river valleys were found in many areas. Images showed that floods of water broke through dams, carved deep valleys, eroded grooves into bedrock, and travelled thousands of kilometres. In the southern hemisphere, areas of branched streams suggest that rain once fell. The numbers of recognised valleys has increased through time. Research published in June 2010 mapped 40,000 river valleys on Mars. Just a wee aside here, a lot of the pictures you're going to see, the slides were taken from orbit by satellites, and if you're not used to looking at geological maps, etc., it's slightly difficult to get it clear in your head what it looks like. So what I've tried to do where possible, is to put a picture from Earth of the same sort of feature, which hopefully if you look from one to the other, it should show the same sort of shapes or structures. Martian waterborne features can be classified into two distinct classes: branch, terrestrial scale, widely distributed valley networks, and exceptionally large, long, single-thread, isolated outflow channels. Recent work suggests that there may also be a class of currently enigmatic, smaller, younger channels in the mid-latitudes, perhaps associated with the occasional local melting of ice deposits. Ancient Mars had significantly higher levels of water than today. This slide shows a major outflow channel named Castle Valles, seen in Mola elevation data. Flows from the bottom left of the picture to the right, running for about 1,600 kilometres. The channel system extends another 1,200 kilometres south of this image to Kadma. Researchers have also found a number of examples of deltas that formed in Martian lakes. Finding deltas is a major sign that Mars once had a lot of liquid water. Deltas usually require deep water over a long period of time to form. Also, the water level needs to be stable to keep sediment from washing away. Deltas have been found over a wide geographical range, although there is some indication that deltas might be concentrated around the edges of the suggested former northern ocean of Mars. Unlike on Earth, there is a suggestion that groundwater plays a vital role in controlling broad-scale sedimentation processes on Mars. According to this hypothesis, groundwater with dissolved minerals came to the surface in and around craters and helped to form layers by adding minerals, especially sulfate, and cementing sediments. In other words, some layers may be formed by groundwater rising up and depositing minerals and cementing existing loose wind-blown sediments. The hardened layers are consequently more protected from erosion. This process may occur instead of layers forming under lakes or the sea, which is the way it normally happens on Earth. A study published in 2011 using data from the MRO showed that the same kinds of sediments exist in a large area that includes Arabia Terra. It's been argued that the areas that we know from satellite remote sensing, which are rich in sedimentary rocks, are also those areas which are most likely to experience groundwater upwelling on a regional scale. And this is a GIF, hopefully you'll be able to see the colour changes here. In August 2011, NASA announced the discovery of current seasonal changes on steep slopes below rocky outcrops near crater rims in the southern hemisphere. These dark streaks, now called recurrent slope lineae, were seen to grow downslope during the warmest part of the Martian summer, then to gradually fade through the rest of the year, recurring cyclically between years. The researchers suggested these marks were consistent with brines, flowing downslope and then evaporating, possibly leaving some sort of residue. The CRISM spectroscopic instrument has since made direct observations of hydrosalts appearing at the same time that these recurrent slope lineae form, confirming in 2015 that these lineae are produced by the flow of liquid brine through shallow soils. The lineae contain hydrated chlorate and perchlorate source, which contain liquid water molecules. The lineae flow downhill in Martian summer when the temperature is about or above minus 23 degrees centigrade. However, the source of the water remains unknown. The polar ice caps are well-known telescopic features of Mars, first identified by Christian Huygens in 1672. Since the 1960s, we've known that these caps grow and shrink according to the seasons, and are composed of carbon dioxide ice that condenses out of the atmosphere as temperatures fall to 148 Kelvin during the polar wintertime. In the north, the carbon dioxide ice completely dissipates in summer, leaving behind a residual cap of water ice. However, at the South Pole, a small residual cap of carbon dioxide ice remains throughout the summer. In July 2008, NASA announced that the Phoenix lander had confirmed the presence of water ice at its landing site near the North Polar Ice Cap. This was the first ever direct observation of ice from the surface. 2 years later, the shallow radar on board the Mars Reconnaissance orbiter took measurements of the North Polar ice cap and determined that the total volume of water ice in the cap is 821,000 cubic kilometres, or about 200,000 cubic miles. That's equal to 30% of the Earth's Greenland ice sheet, or enough to cover the surface of Mars to a depth of 5.5 metres. Both residual ice caps overlay thick layered deposits of interbedded ice and dust. In the north, the layered deposits form a 3 kilometre high, 1,000 kilometre diameter plateau called the Planum Boreum. A similar kilometres thick plateau, Planum Australe, lies in the south. Both plains are sometimes treated as synonymous with the polar ice caps, but the permanent ice, seen as the high albedo white surfaces in the slide above, forms only a relatively thin mantle on top of the layered deposits. The layered deposits probably represent alternating cycles of dust and ice deposition, caused by climate changes related to variations in the planet's orbit. The polar layered deposits are some of the youngest geological units on Mars. NASA researchers have also reported conclusive evidence that these ice caps wax and wane as a result of the tilt and orbit of Mars in a manner resembling Earth. The amount of ice stratified into sand deposits is so significant that if it were melted down, the water would form a planet-wide pool 5 foot deep. Many large areas of Mars either appear to host glaciers or carry evidence that they used to be present. Much of the areas in high latitudes, especially the Ismenius Lacus quadrangle, are suspected to still contain enormous amounts of water ice. Recent evidence has led many planetary scientists to believe that water ice still exists as glaciers across much of the Martian mid and high latitudes, protected from sublimation by thin coverings of insulating rock and dust. In January 2009, scientists released the results of a radar study of the glacier-like features called lobate debris aprons in an area called Deuteronolus Medsii, which found widespread evidence of ice lying beneath a few metres of rock debris. Small diversion here. You might be wondering how we know the various features I've mentioned so far are composed of the materials and chemicals I've stated. The answer is that they're often detected by this instrument. As astronomy fans, you're probably well aware of the use of spectroscopy to analyse the composition of starlight and through the application of redshift to determine how distant stars are from the Earth. This is easily visualised as the light from the star being passed through a prism and the different absorption bands being analysed. However, CRISM is a bit more complex. CRISM measures visible and infrared electromagnetic radiation from 370 to 3,920 nanometers in 6.5 nanometer increments. The instrument has two modes, a multispectral untargeted mode and a hyperspectral targeted mode. In the untargeted mode, CRISM reconnoiters Mars, recording approximately 50 of its 544 measurable wavelengths at a resolution of 100 to 200 meters per pixel. In this mode, CRISM mapped the entire planet over the course of a year. That data was used to identify scientifically interesting locations for further investigation. It was then switched to targeted mode, where it measured energy in all 544 wavelengths. At an altitude of 300 kilometers, CRISM detects a narrow but long strip on the Martian surface, about 18 kilometers across and 10,800 kilometers long. The instrument sweeps this strip across the surface as the MRO orbits Mars to image the surface in the detail required to produce the images we have seen. So far, we've had a look at some of the evidence supporting the theory that Mars had a lot of surface water for all of its history. This was backed up by data gathered from high altitude by orbiting satellites. Let's now look at more evidence, but this time from close-up images captured by Mars rovers. The photograph on the left was taken by the Curiosity rover in 2012 using its Mars camera. It shows a portion of an outcrop of rock similar to the conglomerates found on Earth. The pebbles below the rock are clasts that have been weathered from the rock. The photo on the right is a conglomerate outcrop from near Loch Lomond. So they look pretty similar to me. The presence of conglomerate and sandstones on Mars is evidence of moving water. Wind is not strong enough to pick up pebbles over a centimetre in diameter, even in Mars's lower gravity. To move larger pebbles requires the power of flowing water. The pebbles in this rock show a high level of rounding, which implies a significant distance of transport, which is the geology's way of saying these pebbles must have been lying at the bottom of a river and bounced along for quite a long distance, where all the rough edges got rubbed off and it made them a bit rounder. The red colour is thought to be iron staining, which is nearly ubiquitous on Mars and gives it the name the red planet. The cement that binds the particles in these rocks could be a sulfate mineral. This photograph shows a portion of an outcrop inside the Gale crater. The view shows an area about 1 metre wide. The colour's been balanced to make the scene look a bit more like it was on Earth, as you can see by comparing it with the wee picture. Visible in this image are rocks that are very similar to the shales found on Earth. They're fine-grained, thinly layered, and fissile, meaning they easily break into thin sheets. Rocks on Earth that break this way are usually made up of mud or clay minerals or micrograins that settled out at the bottom of deep lakes. Their plate-shaped grains were deposited on the bottom in a parallel orientation. This gives the rock the ability to be split into thin layers. Clay minerals are known to be abundant on Mars, so it's likely these rocks are composed of clay minerals. This is another photograph taken by NASA's Mars rover Curiosity in 2012. It shows a portion of an outcrop with sedimentary structure, similar to the cross-bedded sandstones found on Earth. When a sedimentary rock that was deposited in nearly horizontal layers has internal layering that is inclined at different angles, the structure is known as cross-bedding. The large-scale layering in these rocks is inclined to the left. However, the smaller internal layers are inclined at various angles. Multiple angles of cross-bedding reveal that the direction of wind or water flow changed over time. The image on the left was taken from orbit by the MRO near Marta Valles. It shows an outcrop of basalt flow with columnar jointing. The image on the right is a photo of the most famous example of columnar jointing on Earth. It's of a basalt flow that outcrops in the Devil's Postpile National Monument in California. At least NASA says it's the most famous, but I've never heard of it. Giant's Causeway, that's famous. The image on the left shows a field strewn with pieces of volcanic rock that are very similar to the scoria found on Earth. The rock in the foreground of the image is about 18 inches across and was found by the Spirit rover. The rock has a rough surface and vesicles, which is small holes, like scoria. Scoria can be thought of as a dense form of pumice that you might have in your bathroom. The holes are formed when gas expands within the magma being ejected from a volcano. And this is a photo of the heat shield rock, the first meteorite ever discovered on the surface of another planet. It's a baseball-sized iron-nickel meteorite discovered by NASA's Opportunity rover in 2005. That meteorite was spotted on Mars, but the only way to study Martian geology until very recently was to examine meteorites that had been blasted off the surface of Mars to be captured by Earth's gravity and fall to the ground here. Over 60 meteorites have been found that came from Mars. Some Martian meteorites, called basaltic shergottites, appear to have been exposed to liquid water prior to ejection into space. It's been shown that another class of meteorite, maclites, were suffused with liquid water around 620 million years ago, and that they were ejected from Mars around 11 million years ago by an asteroid impact. They fell to Earth within the last 10,000 years. In 1996, a group of scientists reported the possible presence of microfossils in the Allen Hills 84001, which is pictured here, a meteorite, definitely from Mars. Many studies disputed the validity of the fossils. It was found that most of the organic matter in the meteorite was of terrestrial origin. In addition, the scientific consensus is that morphology alone cannot be used unambiguously as a tool for primitive life detection. Interpretation of morphology is notoriously subjective, and its use alone has led to numerous errors of interpretation. So you can see that the thing looks like a wee petrified worm, but I saw a program on the telly a couple of months ago that suggested when you're using an electron microscope to bring out the finest details, they quite often spray the sample with gold. And there's a thought that this is actually just a splatter of gold fragments. I'm a bit obsessed with a program on the Discovery Channel called Outback Opal Hunters. I don't know if any of you guys watch it, but I love it. The terrain the miners work in could be on Mars. It's often very bleak and very red rock. However, the traces of opal found on Mars sadly didn't look like the slide. Researchers at Glasgow University examined an Akla meteorite discovered in 1911. Within it, they found 1.5 grams of fire opal with traces of green and red. So it's like the one on the bottom left. Opal is a hydrated silicon dioxide mineral with many astounding properties, but it's also water hydrated. Since the water hydrated minerals have been found on Mars, we are led to the logical conclusion that when these minerals were formed, there was water on Mars. Opals have long been prized for their beauty, but now scientists are appreciating them from a whole new perspective. The fact that they've been identified in a meteorite shows that Mars must have been wet for more than 1 billion years longer than previous estimates. So, I know we've been talking about there being water on Mars, but this is perhaps overdoing it a bit. Hopefully I've now made the case for there being significant amounts of water on Mars in the past, and we're now going to look at some other major geological features. The small aside into the development of geology as a science. After the Second World War, it occurred to the US military that they knew almost nothing about the waters under the ocean, and finding Russian submarines would be easier if they knew more about the geography under the Atlantic Ocean. They therefore embarked on a huge effort to map the ocean floor. They'd also noticed that instruments and submarines often gave erroneous readings, which they thought was due to magnetic anomalies. So part of the mapping was to record the magnetism on the seafloor. The fact that Europe and Africa looked like a jigsaw piece that would lock with North and South America had long been viewed as an intriguing coincidence. In 1912, Alfred Wegener proposed that the continents had once been joined and over time they drifted apart. However, nobody had any proof that this was true. So here's where the story gets interesting. When the data from the seafloor mapping was completed, it became clear that the bottom of the Atlantic contained a barcode that enabled scientists to read the geological history of the formation of the Atlantic Ocean. Stripes form whenever two plates are being pushed apart. So again, hopefully you can read this, but it's different colours. The white's a reverse magnetic polarity here, and the other colours are normal magnetic polarity. What this tries to show is that the stripes on either side are roughly the same size and the same width. That proves that stuff's coming out and being pushed in both directions at the same time. As the plate spreads and cools, it becomes magnetized in the direction of the Earth's strong global field. Since Earth's global field changes direction a few times every million years, a flow that cools in one period will be magnetized in a different direction than a later flow. As the new crust is pushed out and away from the ridge, stripes of alternating magnetic fields aligned with the ridge axis develop. Transform faults, identified by shifts in the magnetic pattern, occur only in association with spreading downturns. So this proved that Wegener was right back in 1912, and the continents were indeed slowly drifting apart on top of the liquid core of the planet. Once GPS came along, we could easily prove that the continents are indeed drifting apart at roughly the same speed as your fingernail grows, about 3 centimeters per year. So back to Mars. As you can see from this slide, especially in the center bottom, similar magnetic stripes can be detected in the crust of Mars. Since Mars lost its liquid core a long time ago, these stripes are fixed, but give a strong indication that Mars once had tectonic activity similar to Earth before it cooled. And here's the same data, but displayed in a more viewer-friendly way. Just let you read the slide for a second or two, I'll catch my breath. Although I've said Mars has cooled to the point where continental drift is no longer possible, some tectonic activity may still occur. The track, about a third of a mile long on Mars, shows where an irregularly shaped boulder careened downhill to its current upright position, seen in a July 3rd, 2014 image from a high-res camera aboard the MRO. The shadow cast by the rock in mid-afternoon sunlight reveals it's about 6 meters tall. In this downward-looking image, the boulder is only about 3.5 meters wide. It happened to come to rest with its long dimension vertical. The trail it left on the slope has a pattern that suggests the boulder couldn't roll smoothly or straight due to its shape. Due to the size of the boulder, some think that this suggests that Mars, like the Moon, is still geologically active, suggesting that the core hasn't completely cooled. On Earth, as plates move over volcanic hotspots, the magma rises and slowly builds up large islands. As the plate continues to move, a second volcano creates a second island and then a third, etc. Volcanic rock erodes easily, geologically speaking, so the original island slowly disappears back under the sea. And that's how we get island chains like the Hawaiian Islands and the Japanese islands that you're probably aware of. It's therefore thought that the Tharsis volcanoes on Mars could have been formed by the same processes, since they lie along a straight line. The main difference being that since there's now nothing eroding them, they're still all huge structures. And talking of huge structures, on Earth, islands and volcanic arcs quickly get eroded back under the sea, and even the mountains of the Himalaya are slowly being worn down and out by the effects of wind and water and ice, even as they're being pushed up by the Indian plate being forced under the Asian plate. It's estimated that the River Indus submarine fan contains about 5 million cubic kilometres of sediment that's been washed down from the Himalayan mountain. Measured from the seabed, Mauna Kea is higher than Everest, measured from sea level. Mauna Kea, as we just saw a couple of minutes ago, will come up from the very bottom of the ocean through volcanic eruptions. If it was on Earth, the massive Olympic muds would cause the crust underneath to crack, as it couldn't support its weight. But since the gravity on Mars is only a third of that on Earth, and it suffers no appreciable erosional processes, there's nothing acting to reduce its height. A third piece of good evidence for plate tectonic events happening in the past can be seen in the Valles Marineris, a large canyon 6 times as long as the Grand Canyon and 8 times as deep. It looks just like a rift formed on Earth by a plate being pulled apart. In fact, it is oriented just as one would expect from plate motions implied by the magmatic map we saw earlier. And here's the Great Rift Valley in Africa, which looks kind of like the Valles Marineris. The Great Rift Valley is forming as the Horn of Africa has been ripped off the eastern edge of the continent as it's being forced against the Arabian plate. Eventually a sea will fill up this gap. We've taken a close look at the history of oceans and volcanology on Mars, and now I'm going to highlight some specific features on Mars, which I hope might be of interest to you. NASA scientists studying pictures from the Odyssey spacecraft have spotted what might be 7 caves on the flanks of the RCM-1's volcano. The pit entrances measure from 100 to 250 metres wide, and they're thought to be at least 75 to 100 metres deep. On the slide, the pits have been informally named as Dina, Chloe, Wendy, Annie, Abby, Nikki, and Jean. No idea where the names came from. Number A is Dina, and it says the floor is observed and found to be 130 metres deep. Further investigations suggest that these are not necessarily lava tube skylights. Review of the images has resulted in yet more discoveries of deep pits. It's been suggested that human explorers on Mars could use lava tubes as shelters. These caves may also be natural structures offering protection from micrometeoroids, UV radiation, solar flares, and high-energy particles that bombard the planet's surface. These features may enhance preservation of biosignatures over long periods of time and make caves an attractive astrobiology target in the search for evidence of life beyond Earth. Holden is a 140 kilometre wide crater in the Margratifer sinus quadrangle. Like some other craters on Mars, Holden has an outlet channel, Uzboy Valles, that runs into it. Some features in the crater, especially lake deposits, seem to have been created by flowing water. The crater's rim is cut with gullies, and at the end of some gullies are fan-shaped deposits of material transported by water. The crater is of great interest to scientists because it has some of the best exposed lake deposits. One of the layers has been found by the MRO to contain clay. As we've said earlier, clays only form in the presence of water. It's suspected that great amounts of water went through this area. One flow was caused by a body of water large in the Earth's Lake Huron. This happened when water burst through a crater rim that was damming it. Holden's an old crater containing numerous smaller craters, many of which are filled with sediment. Indeed, over 150 metres of sediment is exposed in Holden crater, especially in the southwestern part. The central mountain is also obscured by sediment. Much of the sediment probably originated from river and lake deposits. Studies of the whole region around Holden crater have resulted in an understanding of a complex sequence of events that shaped it, which included two other different lakes. A large series of rivers drained water from the Hargari Basin, site of a large lake. When an impact occurred and produced Holden crater, the system was blocked by a crater rim almost a kilometre high. Eventually, water from drainage from the walls, with possibly a contribution of groundwater, collected to make the first lake. This lake was deep and long-lasting. The lowest level of sedimentary rocks was deposited in. Much water was inbounded in the Uzboy Valles because the rim of Holden crater blocked the flow. Some of the backed up water came from the Mugar Valles, which had a discharge of about 4,800 cubic metres a second. At a certain point, the stored water broke through the rim of Holden and created a second, shorter-lived lake, 200 to 250 metres deep. Water with a depth of at least 50 metres entered Holden at a rate that 5 or 10 times the discharge of the Mississippi River. Terraces in the presence of large rocks, tens of metres across, support these high discharge rates. If you think back to what we were talking about earlier with the rounded pebbles and rivers, so imagine how much water you need to actually move rocks tens of metres across. It's a lot. Eridania Lake is a theorised ancient lake with a surface area of about 1 million square kilometres. Its maximum depth is 2,400 metres and its volume is 500,000 cubic metres. It was larger than the Caspian Sea, which is the largest landlocked sea on Earth, and contained more water than all the Martian lakes put together. The Eridania Sea held more than 9 times as much water as all of America's Great Lakes. The upper surface of the lake was assumed to be at the elevation of valley networks that surrounded it. They all ended at the same elevation, suggesting that they emptied into a lake. This slide's a bit difficult to visualise from the orbital data, and the ground here is far too rough to risk landing a rover anywhere near it. So this is the best view we're likely to have for many years to come. The insert shows mesas in America for comparison. Although they're formed from eroded sandstone, the Martian mesas probably look similar at ground level. As the Eridania Lake dried out in the late Noachian epoch, it divided into a series of smaller lakes. Clays which require water for the formation have been found within the borders of this supposed lake. They were identified as magnesium and iron-bearing phyllosilicates and aluminium-rich phyllosilicates. A study published in 2016 found that a capping layer lies above an aluminium-rich clay layer. Beneath this layer is iron-rich clay, called non-tronite smectite, and then a layer of zeolite or hydrated sulfate. Small deposits of alunite and jarosite were also discovered. These clay minerals provide favourable conditions for the possible preservation of past Martian life traces. The mesas on the floor are there because they were protected against intense erosion by deep water and ice cover. CRISM measurements show minerals may be from seafloor hydrothermal deposits. It's suspected on Earth that life originated in hydrothermal vents, so it's possible that life might have originated in the sea. This diagram shows how volcanic activity might have caused deposition of minerals on the floor of the Eridania Lake. Chlorides could be deposited along the shoreline by evaporation. So again, if you've seen pictures of hydrothermal vents on Earth, you see the hot magma bubbling up through the bottom of the seabed. They're bringing a lot of minerals up with it. And these can form sea mounds, as you can see, very bouncy bits. And after evaporation, some of the chlorides get deposited at the edge. Scientists at the University of Glasgow might have discovered how Mars lost its early carbon dioxide-rich atmosphere to become the cold and arid planet we know today from a microscopic analysis of a Martian meteorite. The team discovered that the siderite in the meteorite had formed by the process of carbonation, whereby water and carbon dioxide from the Martian atmosphere reacted with rocks containing the mineral olivine. These reactions then formed the orange siderite crystals, replacing the blue olivine, and in so doing, captured the atmospheric carbon dioxide and permanently stored it within the rock. The loss of carbon dioxide from the atmosphere of Mars around 4 billion years ago is likely to have caused the planet to cool. Understanding how carbon dioxide was removed from the Martian atmosphere could lead to new ways of reducing the accumulation of greenhouse gases in our own atmosphere. Some landslides, both here and on Mars, behave in a puzzling way. They flow a lot further than friction should allow them to. They can also be massive, including a well-preserved one in Valles Marineris that's the same size as the state of Rhode Island. Scientists have speculated that it might be so large because a layer of ice that existed in the past provided lubrication, but a new study suggests that no ice is needed to explain it. Coprati's Chasma is one of the best preserved landslides on Mars. The landslide has ridges that extend in the direction the landslide flow along almost the entire length. In the past, scientists thought that these ridges formed because of the presence of underlying ice. The fact that these ridges have also been spotted on landslides near glaciers here on Earth lent credence to that idea. However, new research suggests that an underlying layer of lighter, unstable rocks could also explain the landslide ridges. The underlying layer would form from the action of the landslide itself, as larger rocks were pulverized. In turn, that would have created a convection process, where the lighter rocks would rise due to the heat, and heavier, cooler rocks would fall to the top of the landslide. A yardine is a streamlined protuberance carved from bedrock or any consolidated material by the dual action of wind, abrasion, dust and sand, and deflation, which is the removal of loose material by wind turbulence. Yardines become elongated features typically 3 or more times longer than wide, and when viewed from above, resemble the hull of a boat. Facing the wind is a steep, blunt face that gradually gets lower and narrower towards the end. Yardines are formed by wind erosion, typically of an originally flat surface formed from areas of harder and softer material. The soft material is eroded, removed by the wind, and the harder material remains. The resulting pattern of yardines is therefore a combination of the original rock distribution and the fluid mechanics of the airflow and resulting patterns of erosion. Yardines can be found in most deserts around the globe. Depending upon the winds and the composition of the deposits of silt and sand from which they're carved, yardines may form very unusual shapes. Some resemble various objects or even people. You therefore have to be very careful not to overinterpret satellite image features on Mars. Remember the face on Mars controversy. The northern and southern hemispheres of Mars are strikingly different from each other in topography and physiography. Simply stated, the northern part of the planet is an enormous topographic depression. About a third of the planet's surface in the northern hemisphere lies 3 to 6 kilometers lower in elevation than the southern 2/3. The southern uplands is very heavily cratered and ancient, characterized by rugged surfaces that date back to the period of heavy bombardment. In contrast, the lowlands north of that dichotomy boundary have very few large craters, very smooth and flat, and have other features indicating that extensive resurfacing has occurred since the southern height was formed. The third distinction between the two hemispheres is in crustal thickness. Topographic and geophysical gravity data indicate that the crust in the Northern Islands, sorry, the Southern Islands, has a maximum thickness of about 36 miles, while crust in the Northern Island peaks at around 20 miles. The origin and age of the dichotomy are still debated. Hypotheses of origin generally fall into two categories. One, that it was produced by a mega impact event, or several large impacts early in the planet's history, or else it was produced by crustal thinning in the Northern Hemisphere, by mantle convection, overturning, or other chemical and thermal processes in the planet's interior. One model suggests that an early episode of plate tectonics produced a thinner crust in the north, similar to what's happening between the spreading plate boundaries and Earth that we saw earlier in the mid-Atlantic ridge. Whatever its origin, the Martian dichotomy appears to be extremely old. Hopefully you found something of interest amongst the slides I've shown you tonight. I find Mars fascinating, since of all the planets, we've been able to examine much of it in fine detail, and very soon, two more exciting missions are due to launch. NASA's Perseverance rover is specifically designed to seek signs of habitable conditions on Mars in the ancient past, and also search for signs of past microbial life. The rover has a drill that can collect core samples of the most promising rocks and soils and set them aside in a cache on the surface of Mars for possible retrieval to Earth in a few years' time. China has announced its first ever independent Mars mission, the Tianwen-1, which directly translates to Quest for Heavenly Truth. This ambitious Mars mission may put China amongst the world's space leaders if it's successful. The mission will not just consist of an orbiter and a rover, but will also include a lander. A Mars landing is considered to be one of the most difficult things to achieve. China's mission is set to launch in July this year. So far, it's been a total of 18 Mars missions, comprising either landers or rovers, but only 10 of them have been successful. And out of those 10, 9 have been sent by NASA. I hope I'm around long enough to hear that there's indeed some evidence that life of some description has been found, at least in the fossil record, preserved in a sample examined by one of the rovers. So, as I said earlier, hopefully you found something interesting in that. And if you've got any questions, now's a good time to start.